also would be like, I think that Antonio and me for local. Sure. Yeah, I think that doesn't make sense. We do have 4 microphones because it doesn't make sense when she answers everything about the local organization. People complain about the wireless.
So is this important? Like, do you need to make sure that somebody complains about the wireless? Like, do you need me to complain about the wireless?
You can know. I guess someone will do, and then I can answer that. And maybe for
Ladies and gentlemen, it's my pleasure to chair the last technical session before the posters of RSS. And it is also my distinct pleasure to introduce our speaker, Marco Pavone, one of our 2 early career spotlights. I've known Marco for quite a while. He was at MIT, and even when he was a graduate student at MIT, his work, received tremendous attention in dynamic vehicle routing. His thesis defense was one that the faculty went to even when we weren't on his thesis committee, which, knowing faculty and how they tend to pay attention to things, is a remarkable testament to his research. After Marco got his PhD in 2010, he went to JPL and was a research scientist there, and then moved on to Stanford, where he continued to do tremendously good work in developing an understanding of what makes systems safe. He also continued his work in planning. I mean, Marco is now one of the leading lights in both basic motion planning. His FMT algorithm is one that I think most of us, that paper by him and his students is one I think most of us have read, and has also continued to do branch out and explore new areas, which I think is also, that ability to branch out and move into very different areas is obviously the hallmark of a curious mind and a tremendous scholar. So with that, I will shut up and turn the stage over to Marco. Welcome.
Thank you, Nick. Thank you very much for the nice introduction. And it's an honor for me to give this talk. So my lab broadly focuses on the design of planning decision-making algorithms for robot autonomy, basically on how to make robots capable of making decisions on their own. One of the key application domains is indeed space robotics. Specifically, as a research scientist at NASA JPL, I work on optimizing the entry, descent, and landing of rovers on the surface of Mars. I've also been working on the design of robotic mobility platforms for the exploration of very low gravity bodies, such as asteroids and comets, where traditional mobility systems based on wheels do not work well anymore. And on top of that, the complex topography of the environment makes mobility very difficult. For example, here, I show the typical surface that you would encounter on a comet. In particular, in collaboration with JPL, we have designed internally actuated hopping robots, which we tested in a microgravity testbed that we developed in my lab. Currently, through a collaboration with NASA Ames and Mark Kutkoski's group at Stanford, we're working on planning and control techniques to grasp and manipulate objects in space. Here, I'm showing tests at NASA Ames where zero gravity is emulated by using air bearings of a very flat granite tables. The arm is equipped with a gecko-inspired gripper that is a gripper equipped with pads that exploit directionally aligned macro features in order to become adhesive when loaded in shear stress. A flight-qualified version of this gripper is going to be launched next month on July 21st on board the SpaceX 18 cargo mission for testing later this year. Now, in all these applications, increasing the level of autonomy is extremely challenging due to a combination of the uncertainty of the environment coupled with often the stochastic dynamics of the platform itself, like, for example, for hopping in very low gravity bodies like asteroids. However, as a redeeming factor, in space robotics, one does not have to deal with the intelligent forms of life, that is, humans. Interacting with humans is indeed a critical challenge for robot autonomy, and indeed it will be the focus of this talk. In particular, consider the case of driving, that of course is receiving a lot of attention from industry nowadays. In particular, consider this case where vehicles are trying to merge onto the highway, exiting from the highway, and so on. Despite the fact that the overall goal of each one on the road is clear to everyone else, there is a lot of uncertainty in the outcome of the interaction, which depends on a very complex and sometimes quite aggressive negotiations. In general, this video showcases how interactions on the road, interaction in general, are really an exercise in negotiation. An autonomous system should be able to perform such negotiation for safe and efficient operations. In other words, autonomous systems should be able to perform what I refer to as a proactive decision-making. That is, to proactively interact with other agents in order to infer their intents, while concurrently exploit this information to take actions that anticipate possible responses. Now, my key approach to enable proactive decision-making is model-based, in that probabilistic understanding of the interaction dynamics are exploited as a basis for policy construction. This is in contrast to model-free approaches, whereby the possible actions of a human and relative likelihoods are only implicitly encoded in a policy that is learned directly from data. And I advocate that this separation between intent prediction and policy construction achieves a level of transparency that is typically very difficult to achieve with model-free approaches. And this point is done and highlighted in a very insightful paper from Anka's group that just came out. Now, within a model-based approach, the first step in order to enable interaction-aware decision-making is to have modules that allow us to infer the intent of a human. And my work on intent prediction is guided by 5 guiding principles. The first one is that we would like to have an intent prediction framework that allow us to predict the intent of a human conditional on candidate robot actions. Second of all, we are targeting time scales on the order of 1 second. This is different from high-level reasoning that usually takes into account macro actions. And is also different from low-level collision avoidance that usually needs to operate on the time scale of milliseconds. Third, on these time scales, human behavior is highly multimodal. So we want to have a model that is flexible enough to capture the multimodality of a human behavior. For example, in this lane swapping case, if the robot were to accelerate, the human might either decide to decelerate, but with low probability might decide to accelerate. And we want to capture these 2 drastically different modes. We want to be able to capture the history of interaction in order to uncover latent behavior like alertness or aggressiveness. And finally, we want to have a model that is interpretable. Now, to infer human intent, typical approaches such as, for example, inverse reinforcement learning that are referred to as ontological or theory of mind postulate some structure on how humans make their own decisions. For example, in terms of a cost function that a human is trying to optimize. But this postulated structure sometimes is difficult to reconcile with how humans actually operate and particularly drive. Usually, in general, are not cooperative, nor they're adversarial. And such fuzziness of behavior is difficult to reconcile with a model that is rooted in cost optimization and game theory. We have thus investigated whether, given enough data, we can build a phenomenological model that allow us to reason about possible human actions and corresponding likelihoods without making any structural assumptions on how humans do their own reasoning. Basically, without reasoning about the underlying motivations. To do that, we had to gather interactive driving data, and to do so, we built a testbed in my lab where students drive in a variety of interactive scenarios, for example, intersections, lane swapping, and so on. Now, from a technical standpoint, there has been a lot of work recently on generative modeling from the human community, basically how to predict the future. Where our work differs from the norm, though, is that we want to predict the future not only based on the past, but we also want to reason about how a human would respond to a candidate robot action. In particular, we want to learn an action distribution conditioned on the past of on the history of the interaction, for example, in terms of relative speeds and relative velocities, but also conditional on a future robot action. Conditioning on the history of an interaction allow us to uncover latent behavior like, for example, aggressiveness. And conditioning on the future allow us to capture the interactive aspects of an interaction. Practically, we learn such a distribution by using a conditional variational autoencoder. And we use the conditional variational autoencoder to generate possible human responses to candidate robot actions. For example, in this example, on the x-axis, we have time. On the y-axis, we have longitudinal acceleration. Solid line means that something has happened in the past. Dashed line is the future. So the idea is, well, if the robot, so we start from an initial condition where the speeds are constant. Acceleration is equal to 0. And then we ask the intent prediction model the following equation. If the robot were to enact an acceleration profile whereby we accelerate, we go a steady state velocity, and then we decelerate, what are the possible responses from a human? Each color here corresponds to different modes of the probability distribution related to different values of the latent variables. So we use this prediction model as the basis for policy construction for an autonomous car. In a nutshell, what we do is to consider about 4,000 motion primitives, and for each one of them, we generate a number of possible responses from the human by using the CVAE-based model that I discussed before. In total, we generate at each planning cycle about 100,000 possible scenarios, and we do that at about 3 to 4 hertz by leveraging a parallel implementation. We score the best action sequence by considering an aggregate cost function that accounts for collision avoidance penalties, task fulfillment, and control effort, and so on. And we average the scenarios, and we take the motion primitives that achieve best performance. Now, natural question is that in scoring the motion primitives, we look at average performance. One might be interested in infusing notion of risk sensitivity, since we are dealing with a safety critical system. Now, infusing risk sensitivity in a probabilistic decision-making framework is actually a quite tricky topic that I won't go into for the purposes of this talk. But I actually have a position paper that appeared about a couple of years ago that illustrates the challenges of risk-sensitive decision-making from modeling standpoint, from a computational standpoint, and for an interpretability standpoint. And I'll be happy to talk to you later if you're interested. Going back to our probabilistic decision-making stack, we tested the algorithms by considering human-in-the-loop testing, whereby a human drives in a simulator. The car driven by the human is depicted in blue, and the car driven by our algorithms is in white. On the left-hand side, so we consider the task of swapping a lane, and on the left-hand side, you can see predicting human responses to candidate robot actions. You can see that the interactions that emerge appears quite natural, and some interesting behaviors emerge. For example, the white car, the robotic car, nudging onto the other lane to disambiguate the intent of the human. So all of this looks great until disaster happens. As you can see here, at some point, the human defies the prediction of the robotic car and swerve into the robotic car. And of course, there is a collision. Now, I advocate that in a probabilistic setting, it is essentially impossible to avoid such a situation for a number of reasons. First of all, probabilistic guesses are still guesses, and sometimes the intent prediction model can guess it wrong. Second of all, at this level of decision making, usually collision avoidance is encoded as a penalty function among several other cost functions. And this may lead to conflicting objectives. And finally, for safety, replanning at 3 or 4 hertz is ultimately too slow. So the key question is then, how do we integrate a probabilistic decision-making module that is aimed at efficiency performance with a low-level safety-preserving module, which necessarily reasons more adversarially and is aimed at promoting safety? Or in other words, oftentimes people talk about safety, and when companies try to boast about their performance, they say that the disengagement rates are, say, one every 11,000 miles and so on. But without telling the other part of the story, what is the impact of that extreme safety in terms of efficiency is very difficult to gauge the benefit of an autonomous system. In particular, high-level planners typically are aimed at promoting efficiency, sometimes at the cost of safety. Low-level planners are aimed at promoting safety, sometimes at the cost of efficiency. Of course, one would like to be here, where we have a maximum efficiency, maximum safety, but usually that is not possible. So the question is, how do we fill this gap? Or, in other words, how do we find a principled way to glue a low-level safety controller aiming at promoting safety with a probabilistic decision-making module aimed at promoting efficiency? I claim that in the literature, the gluing of these different layers in the autonomy stack is often overlooked. So here I'm going to discuss how we can reason in a fairly principled way about how to glue these two different layers of the autonomy stack. Let me first discuss the design of the safety controller, and then we will discuss how to glue it with the probabilistic decision-making module that I explained before. Specifically, there are several approaches to promote safety at a low level, like, for example, potential function, constraint optimization, emergency motion primitives, and so on. But all these techniques do not account for interactions with a sentient agent. And thus, they're difficult to glue with a probabilistic decision-making module that is aimed at performance. So in our work, to account for interactions also at the controller level, we harness the tools of Hamilton-Jacobi reachability. Now, typically, Hamilton-Jacobi reachability is interpreted in the forward sense, meaning that the dynamics of the other agent on the road, in this case the human, are forward propagated in time, and the resulting set is considered as an obstacle, that's a static obstacle that you don't want to enter into. This usually leads to a very conservative formulation that, yes, would promote safety, but from an efficiency standpoint would be concerning. What instead we harness is the notion of backward reachability, whereby the joint dynamics are propagated backward in time, accounting for the closed-loop interactions between the two vehicles. In particular, the resulting set that one obtains encodes the notion that you don't want to put yourself in a situation you cannot recover from despite your best effort. And I like to use the analogy of how differently I drive my motorbike with respect to how I drive my car. When I drive my motorbike, I'm very careful not to put myself in a situation whereby I might be boxed in. And if someone is distracted and is swerving to me, I don't have an opportunity to stop in a safe position or actually have some collision avoidance maneuver. So that's really the reason, the interpretation of backward reachable set. Specifically, a backward reachable set is defined as a set of avoid states for which there exist strategies for the human that for all inputs of the robot will lead to a collision. practically, this set can be computed by solving the Hamilton-Jacobi Isaacs partial differential equations, whose solution, denoted here with phi, referred to as the value function, gives the backward reachable set as its sub-zero level set. PDE, horrible, because of course is computationally intense, but all of this actually can be computed offline. Now, the optimal avoidance controller then is to compute the control for the robot, U star of R, that offers the maximum increase in the value function subject to worst case responses from the human. And the previous application of Hamilton-Jacobi in the context of collision avoidance switches to this controller when the dynamics are near the backward reachable set. Unfortunately, such switching, hard switching, might give rise to very conservative behavior. In this case, the green was the human car, the red was the robot car. This is a case where operations were safe. The robot car stopped once it detected that the human was swerving into the robot car. But of course, from an efficiency standpoint, this was terrible. Think of cars as mobility machines. You don't want to stop every few meters because there is a slight chance of being in a collision. So the key idea to better glue Hamilton-Jacobi inspire low-level collision avoidance with the high-level reasoning is to instead reason in terms of safety-preserving controls. Specifically, I define the set of safety-preserving controls as the controls for the robot UR that ensure that the value function is non-decreasing. Now, the ensuing set is unfortunately leads to problems that are highly non-convex and difficult to solve in real time. So what we do is to linearize these sets around the operating conditions. Now, the low-level control then takes the form of an MPC low-level control algorithm whose formulation is quite standard. We want to penalize tracking error with respect to the trajectory computed by the probabilistic decision-making planner, while also accounting for control effort under the constraint of linearized dynamics, control constraints, stable envelope driving constraints, and so on, but with a critical inclusion of an instantaneous safe interaction safety constraint when near the backward reachable set that ensures safety in terms of, in the sense of Hamilton-Jacobi reachability. So the overall control stack accounts for a probabilistic decision-making planner that predicts the intent of a human by using a conditional variation autoencoder, a reachability cache that encodes the notion of relative states that are unsafe, and a low-level MPC controller that computes actions that are minimally interventional, meaning that minimally deviate from the trajectory that the high-level controller would like to execute in order to promote safety in the Hamilton-Jacobi reachable, Hamilton-Jacobi sense. So we test the full stack on drive-by-wire self-driving car here. And the role of the human-operated vehicle is taken by an RC car. The must that you see here is to make the RC car visible from the LiDARs that are mounted on the robotic car. The reason why we use an RC car that is teleoperated as opposed to a full-scale human car is that we're trying to perform a test at the abuse of our algorithms in order to see what is the breaking point of our algorithms. So of course, to ensure the safety of the students and also the safety of the car, we prefer to, in case, collide with an RC car. So here you see a typical run. When we do prediction, all of a sudden, the human behaves in erratic behavior, swearing to us, and we fairly smoothly recover by carefully controlling acceleration and steering. This is, let's look a little bit closer at the resulting trajectories. The green car is the RC car, human operated. The red car is the robotic car. The blue trajectory is the trajectory corresponding to the controller that I'm proposing. The red one is the path that the car would execute if there is no low-level collision avoidance controller. And the yellow one is the path that the car would enact if it were to switch to the optimal Hamilton-Jacobi controller. As you can see, the notion of safety-preserving controls achieves is basically middle ground between no consider low-level control and being extremely conservative. Here I'm plotting the value function that basically encodes the notion of safety. On the x-time, we have time. On the y-axis, on the x-axis, we have time. On the vertical axis, we have the value function. Negative means that we are in an unsafe situation. Positive means that we are safe. If you look closely, actually, even with our controller, which corresponds to the blue curve, we dip slightly below 0, which you might say is a bit concerned. I was a little bit concerned when I saw that. The reason why we dipped a little bit below 0 is that in our models, we did not account for the slew rate of the front tires. The reason why we didn't do that is that that would add an additional state to our model. And since Hamilton-Jacobi computation that do not scale well with dimensions, we said, okay, maybe we can just get rid of that state. Actually, that was not the case. So since then, we have accounted for the test. We've been a little bit more patient in computing these sets. And this pathological behavior are no longer there. But this is an example where actually doing a real-world experiments really help in refining models and in verifying assumptions. So let's get back to what I shown before, basically the trade-off between safety and efficiency, by looking at experimental data. So here, the blue dots correspond to the implementation of a controller where we only use the probabilistic decision-making module, but no low-level safety controller. Here you can see that the performance is, in general, efficiency measured in terms of G-forces is high, but sometimes we get into unsafe situations. If instead we consider hard switches to the optimal Hamilton-Jacobi controller, in general, we are safe, but this is at the cost of efficiency. Well, the controller that the decision-making stack I'm proposing basically fills the gap between safety and efficiency. Now, we're working on a number of extensions to make this model extremely general. For example, so far I've been considering a pairwise interactions. We're scaling this model to intent predictions in the presence of multiple agents by essentially merging conditional variation autoencoder with techniques from spatio-temporal graph modeling. At the control level, we're also working on extending Hamilton-Jacobi reachability to multiple vehicle setting, where now you have to be very strategic in not putting yourself in a situation where you are boxed in by several cars and maybe a wall. But even more interestingly, we're working on finding ways to increase the amount of conditioning variables that we consider for intent prediction. In particular, one of the advantages of a deep learning model is the ability to work with multiple forms of data, for example, visual data. In particular, currently we're working on incorporating road information and map information into the conditional model. Basically, the idea is to take a map and then encoding in order to get a representation of that map, and then feed this representation into the prediction network at the same point where we feed the other conditioning variables. And finally, we're also considering studying ways of including techniques from symbolic reasoning at a lower level of control in order to reason in terms of rules of the road and other type of constraints. Now, as a final point of discussion, I would like to say that the intent prediction model that I've just discussed is an example of a data-driven model that is designed specifically for the purposes of control. And more broadly, in my lab, we are interested in understanding the theoretical foundations for learning models that are cognizant of the downstream applications. To be concrete, let's consider a relatively simple task, meaning the task of trajectory stabilization, whereby we assume that we do not know the dynamics of the robotic vehicle. So typical model-based reinforcement learning algorithm takes the following approach. We observe trajectories, we record triples in terms of states, controls, and next states, or state derivatives, and then through regression, we estimate the model for the dynamics, and then we use that model in order to generate trajectories that then the robot can follow. But in this procedure, there is nothing that guarantees properties such as controllability or even stabilizability of the model. What guarantee do we have that the model that we learn is a model that generates trajectories that can be tracked? So, in our work, we revise the traditional notion of a model learning, which seeks to minimize regression loss by introducing a constraint. The constraints enforces that the trajectories that are generated by the model are trackable through a feedback tracking controller. basically enforcing such a constraint drastically prunes the hypothesis space and plays the role of a control theoretical regularizer that is more pertinent to the downstream application of control of trajectories. In particular, in this example, we leverage techniques from contraction theory that allow you to turn stabilizability constraints into a set of LMIs. So in this talk, I presented a phenomenological approach for intent prediction, and I discussed how the notion of safety preserving controls allow us to infuse safety as a hard constraint while minimally impacting the performance of a higher level, smarter planner that is aimed at efficiency. As a few general thoughts and lessons learned, I like to point out that a number of underlying themes in this presentation. The first one is that all the models that are presented were carefully engineered for the purposes of control. And I think that this viewpoint of learning models for being cognizant of the downstream application is extremely important for future robotics research. Second of all, and this is a point that was made also very well by Angela, I think there are a lot of opportunities in trying to infuse data-driven models in control theoretical formulations in order to harness the rigorous way of thinking stemming from control formulations and also the safety assurances with efficiency that is typical of learning-based approach. And finally, and this is actually a concern that I deal with every day, is to try to design models that are as simple as possible. This is a rule of thumb in control. In order to have robust performance, one should always use the model that is the simplest to do the job. Oftentimes, people use as an aphorism the fact that all models are useful and some of them are wrong. But they forget the second part of the aphorism by George Box, that is, and, there is an and that people forget, over-parameterization is often a mark of mediocrity. So I think that an important direction for future research is try to understand how to judge in a principled way if the model is the simplest possible one that does the job for the task at hand. So with that, I would like to thank my collaborators, former PhD student Ash Merlin, Karen, Boris, former postdoc Mo, that is currently in Canada, collaborators from the Dynamic Design Lab, John Talbot and Chris Gerdes, and master students that have done the thesis in my lab, and of course my sponsors. With that, I'll conclude my presentation, and I'll be happy to answer any questions you might have.
Thanks, Marco, for that great talk, and I love the final message. What kind of a world would it be that we lived in where all our models had millions of parameters? It would be crazy.
And it's amazing how people forget the whole point of that aphorism by George Box that everyone cites is avoid over-parameterization, why it's a little bit lost in translation.
Fewer parameters. Very good. Questions for Marco?
Okay, I have two questions.
Yeah.
I have two questions. So the first question is going back to the human models. So on the human model side of things and the interactions, you're kind of taking a very model-free approach for just learning the model of the human, right? So the question is, well, how...
But we still learn a model. So this is different from model-free, where basically the...
So you have the human model afterwards, but just the human modeling part of it. So how accurate are these models in general if you think about more complex settings? Like, do you think this should be the way to go? And have you compared this with more game theoretic ways of thinking about the pairwise interactions? Like how would you
that's an excellent question. And indeed, I think one of the key missing topics in this line of research. How do you judge if the decision-making module that relies on intent prediction is better than another decision-making module? It's very difficult to come up with metrics that allow you to make those comparisons. So yes, we have made comparisons with the more game theoretical formulation, and it turns out that basically game theoretical formulations tend to be more conservative, so they are more toward the left in the plot that I showed. But this is something that we should work more on it. I think that an interesting first step has been taken by Anka in the paper that I mentioned, where she, advocates model-based approach, but she makes a difference between more black box approaches that do not postulate any assumption how humans make decisions, and more inverse reinforcement learning approaches. And the general conclusion, that is also what observed in my work, is that in the low sample regime, actually inverse reinforcement learning approaches tend to work well, also in terms of generalization, simply because by placing more structure, actually you require less samples in order to train. But in the regime of a high sample count, eventually black swan models, like the one that I've been advocating in this talk, eventually outperform IR.
What is the accuracy right now, right, like for the human model?
So it depends a little bit on the metric that you use, but we're talking about 20, 30%. Yeah, depending on the sample count. Yeah.
Can I ask another clarification question?
Yeah.
Quick? So then, so when you're doing the planning, you're using MPC, right? Why does it still like hit, right? Because like if you're making the so like the example you were showing where the two cars were actually like colliding, I wasn't sure, like I didn't fully understand why it still collides. Is it just it doesn't have enough time to replan? Because when you're doing your reference trajectory following, you are doing model predictive control, so you could technically replan and get out of the two cars hitting each other.
So when I showed the two vehicles colliding, this MPC tracking controller was not there. So that's why basically the human acted in a way that was auto-sample, and then the vehicle was caught by surprise, and then was not able to actually get. Because basically, at that level of decision-making, you encode safety as a penalty. But it's one cost amidst many other costs. So sometimes it's very difficult to come up with the weights in order to avoid corner cases as the one that I show, where you have collisions. One of the reasons why I like this MPC formulation is that this is usually the formulation that many people in the field really use for low-level control. So actually, what we do is a fairly simple modification to a control paradigm that is already widely accepted by the industry in order to better glue low-level collision avoidance with a high-level probabilistic decision-making. So basically, it also leverages a legacy in the field of autonomous systems, which I think is a figure of merit.
Okay, we got time for one more question. Dieter. Okay, we'll do two more. Dieter first, and then one at the back.
We're here. Thanks a lot. Very nice talk. I was just wondering about scalability. So you could imagine you might apply the same techniques, let's say, for human-robot interaction, a person and a manipulator working in the same workspace.
We're considering that.
And then you go higher dimensional spaces, human skeleton, and maybe the action space also much more complex. Do these techniques relatively easily scale to these dimensions then, or are there issues?
Yeah, so so there are two aspects to that. So one is how quickly we can generate samples from the model. The other one is what is the sample complexity to train these models. So we don't have neither a theoretical nor a practical answer to the question. That's a very good one. One of the reasons why I think these models are promising is that you can inject much higher dimensional conditional information in the model beyond just relative states. So for example, even images whereby in principle the model might be able to pick up information like the angle of the head with respect to the body, maybe the, information about the eyes and so on. So by looking at the parallel result for mainstream machine learning, we are relatively confident that these models would scale to such high-dimensional information. But so far, for us, high-dimensional has been to add the map of the environment. But, and we haven't hit, actually, we can still do computation at 3-4 hertz. And we can still train with a decent, not exaggerate amount of data. But no, it's a very good question. We don't have another theoretical nor practical limit to what extent the models would break. At the same time, of course, one has also to look at alternatives. What would be the alternatives if we really hit that sample complexity regime?
All right, the gentleman at the back gets the very last question of the conference, the last technical question.
So I really like the way y'all used the Hamilton-Jacobi reachability for the relative state to do this collision avoidance. And you'd mentioned that you're moving to a multiple agent version of that. since the state is written as relative and you have to consider it for those two vehicles, could you give us some insights into how you start to extend that to other or to more vehicles without blowing up the number of states?
Right, very good question. So currently, we use a 6-state single track model for the car and a dynamically extended Dubin's vehicle for the human. So when we write these two systems in relative coordinates, we have 7 variables. We also consider the slew rate. Actually, we have 8-state variables that for Hamilton-Jacobi reachability computation, if you do it in an exact matter, is already pushing it. Clearly, the moment you go to more agents or maybe static obstacles, that is beyond the reach of exact Hamilton-Jacobi solvers. So we're looking in collaboration also with colleagues at Berkeley on two parallel, two orthogonal axes. One, to consider more approximate algorithms for reachability computation, more like sampling based. And the other one to look at ways to carefully decompose the problem without excessively lose the coupling between the subproblems. And this is very much something that we're working on right now. So, and if you're interested, I'll be happy to discuss more, this aspect in more detail later on. But it's great, great point. And indeed, really the research question we're addressing right now.
All right, on that note, I'd like to thank Marco again.
Thank you.
And conclude this session. So we have a poster session from now until 5 o'clock, and then at 5 o'clock, we'll all reconvene back here for award ceremony and the town hall.